Okay, looks like the recording's going. Welcome in, ME2001, 2 o'clock, Friday afternoon. Hopefully you're not sick of the week yet. And pay attention for the next hour to your favorite class. Yes. All right. Today we're going to continue force moment relationships. And you have a homework on force moment relationships, which is due next Wednesday. You should be able to make your way through, I'd say, most of that at this point. All right. We did an example problem last time that looks a lot like number 1 and number 2. And number 3 and number 4 are just kind of like 3D extensions of that. So I should be able to do everything at this point. Okay. Well then, let's pick up where we left off. Get my notes here. Bam. Okay. So when we left off, we were working through an example, and specifically it was this guy here. So we were finally using all of our cross products and position vector, force vector information to actually calculate the moment of a force at a particular point on a rigid body. So here we have like this rigid frame here, this L bracket that's coming off of the wall at point B, and we've got some 800 Newton force that's applied to it. And so we worked through this problem to calculate what was the moment at point B, given this particular setup. We said that our moment is the position vector arriving at A from B crossed with the force that exists at A. It's our general cross product equation for the moment. We define our position vector arriving at A from B with this position vector here, and we're going to cross it with the force that exists there at A. It's this 800 newtons. So we have to define both of these in rectangular coordinates. So we did that. Here's like the position vector of A with respect to B. And here's our force at point A. So we execute our cross product using our little determinant setup, or as Ms. Grace likes to say, the chart thingy. The page said the chart thingy. Yeah, that's nice. I like that. And so we're using this chart thingy here and making our way across it to come up with actual moment. And we notice here in this particular problem that the moment happens to be entirely in the z direction. And that sort of makes sense after we go through our calculation with what we know about the cross products, and that our position vector is in this particular plane, this xy plane, and also our force vector is in this plane. So when we take the cross product between the two, we know that our cross product is going to be in a direction that is out of plane with the two vectors that we have. And so the out of plane direction here is the z direction. And we see that after we execute the math, we do in fact have a moment that is entirely in z. And remember how we sort of like think about this moment is it's sort of obeying the right-hand rule, where our thumb will point in the direction of the moment. So if you thought about pointing your thumb in the direction of the moment for this particular problem, you'd be pointing your thumb in the negative k direction. So if you want to maybe think about what that would look like, if I'm kind of at this bracket here and I sort of stick my thumb into the page at point B and I curl my fingers naturally in the direction that would kind of have that inclination, I would think about the bracket trying to kind of like curl in what looks like the clockwise direction in this particular situation. And if we thought about how this particular force might get point B to sort of like twist, you would think that that 800 Newton force would try to sort of like create for myself a clockwise motion of this particular bracket. And so we see that the motion is occurring, or the moment is occurring sort of in this negative k hat direction, which is sort of like this clockwise twist. And so that's kind of a nice thing to see with our example here. Okay, now I want to teach you some shortcuts on how to calculate these moments, because there are easier ways and faster ways, especially in 2 dimensions, for calculating this particular moment. And the chart method there, or the determinant method, is nice and will always work. So if you're comfortable with that and you want to do that and skip out on the shortcuts, that's perfectly fine. And especially if you're like unsure how to go about shortcuts and you're not quite confident in it, then just go with the chart method. It always kind of like works, the determinant method. But I'm going to now talk about some shortcuts and some faster ways that you might be able to calculate moments, given some information you might have about your certain setup. Okay, so let's do shortcuts for moment calculations. Okay. So remember, if we're calculating the moment of a force about a certain point, that we have something like the position vector crossed with the force vector. So if you have some rigid body that exists in space, my world famous like mechanics potato is an example. Okay. And you've got some point that exists inside of this object. Let's call it point O here. And you've got another point that exists on this object where a force is acting. Let's say over here. Here's point A. And you've got a force that's acting at that particular location that might be that direction. Okay, so here's a force that exists at A. Okay. Now, if I wanted the moment about point O that force A generates, we know with our definition that that moment about O is the position vector which arrives at A from O crossed with the force at A. All right, this is how we would use that nomenclature. Where my position vector that arrives at A from O is something like this. All right. Now, I'm going to do a little bit of trickery here and extend some of our forces and extend some information here so we can look at some angles. Okay, so let's extend sort of the line of action. We know this vocabulary term now, of this position vector. And we'll extend the line of action of this force. All right. And we'll notice here that there is an angle that exists here between what is the line of action of the position vector and the line of action of the force at A. And we know that that angle here, or let's say that that angle here is the angle theta. All right. I know the magnitude of my moment is the following. The magnitude of O is the magnitude of the position vector multiplied by the magnitude of the force times the sine of the angle between them. Okay. Now, here's where some of the trickery comes in. All right. If I were to like look at this picture a little bit more carefully, I could see that there's like a right triangle that I could sort of make in space here. And that right triangle looks something like this. Here, right? Where this angle is also the angle theta. I don't think I have the space to draw it. Okay. But this is a right triangle. And for now, I'm going to label this particular leg of the triangle as little d. All right. If I know that the angle that exists between the force and the position vector is this angle theta, then I can sort of use concepts of typical right triangles or use concepts of trigonometry to sort of define the magnitude of the position vector and the sine of the angle theta. Well, this here is d. Okay. If we look at our sort of right triangle there, here. So the magnitude of this particular vector, my position vector RAO, is basically like the hypotenuse of my right triangle that I've just created. And so the hypotenuse multiplied by the sine of the angle theta would give me this sort of little d here. So alternatively, what we can do is write that the magnitude of the moment at O is simply the magnitude of the force at A multiplied by this little d, where d is equal to the magnitude of the position vector times the sine of the angle between the two. Right? Okay, that's nice and that's useful. So one last piece of information that is probably the most important piece of information is that we noticed that this d variable is the perpendicular distance from O to the line of action of A, or the force at A. Okay. So what that means is, if you happen to know the perpendicular distance between the line of action of the force and where you're taking your moment, then you can simply calculate the magnitude of the moment as that perpendicular distance multiplied by the magnitude of the force. So you can find this magnitude quickly. And it's just d times the magnitude of F. So it's if it's an 800 Newton force, and you happen to know the perpendicular distance to the line of action, quick calculation, right? Once you have the magnitude, you can get direction with right-hand rule. Okay. So it's a nifty little trick. This is very applicable when it comes to like forces on a beam. Okay. You have this very long beam and you have a force at one end that's vertical on that beam, and you care about sort of the moment at a point that's over here. Well, if you know the magnitude of this force and it's running perpendicular to your point of interest over here, then whatever that distance is multiplied by that force is the magnitude of your moment. Then use the right-hand rule to figure out its direction, and away you go. You figured out what the moment is at that particular location from that force. Very cool, very slick. Okay, so let's go through an example actually here. And we'll calculate the moments associated with this particular example using kind of traditional methods and also using our shortcut methods so you can sort of see both situations. All right, so let's do an example. Okay, just gonna bring this in. So I'll give you a second if you're working through this to copy this down. Okay, so let's give this guy a go. First, we're going to do traditional moment calculations. Okay, so if we want the moment about this point here, it's point A, from the 20-pound forces, then we're going to have to add the contributions from each one of those separately. So what I mean by that is our moment at point A is going to be, with traditional calculations, the moment from this first force, that would be the position vector arriving at B from A, crossed with the force at B. That is the contribution from that guy there, where the position vector RBA is this position vector here, arriving at B from A. Sorry, it's a little sloppy. Okay, there you go. Position vector arriving at B from A. And I'm going to add to this the contribution from this 20-pound force, which is the position vector arriving at C from A, crossed with my force at C. All right. Or again, my position vector that arrives at C from A is here. Here's R, C, A. Okay. Well, let's define each one of these things. I think it should be pretty straightforward. And then we'll do the calculation. So first, my position vector, which arrives at B from A. I'm going to need a coordinate system to work my way through this, and I think just the traditional coordinate system is nice here. So there's our little XY coordinate system. Make sure we're all on the same page with the proper coordinate system. So my position vector arriving at B from A, well, like I said before, it's just this guy here. So all I need to do to get to B from A is 10 inches in the I direction. My force at B, here I am, 20 pounds, and that's going downwards. So this will be negative 20 J hat pounds. I can continue. My position vector arriving at C from A. Again, that's here. So it looks like I've got to go 10 plus 3 in the I, and I've got to go minus 3 in the J. And lastly, my force at C, that's here, 20 pounds, pointing in the negative X direction, so negative 20 I hat pounds. Okay, so let's go through the full rigmarole here. So the moment at A, if I sort of use my determinant notation, I have two cross products to execute here. Okay, so for this first guy, I have the position vector arriving at B from A, crossed with the force at B. So I can put those into my determinant form directly. So here I have 10, 0, 0 inches. And the force at B be 0, negative 20, 0 pounds. I'm going to add to this the other moment that I have here. Which is going to be RCA crossed with my force at C. Okay, so here I have 13, negative 3, 0. -20, 0, 0. Here, this is inches, and this is pounds. This is sort of my traditional calculation. Okay. So I go through the process here. I'm kind of going down my diagonals. Okay, nothing here, nothing here. I will have something in the k here. So -20 times 10 in k hat. It's going to be -200 k hat. Here, this is inch pounds. And I'm going to add to that the contribution from the other guy. Here I go sort of down into the right. All right, nothing. J down into the right. Again, I run into a 0, so nothing there. K down into the right. I run into a 0, so nothing there. Now I have to go kind of down into the left, so I 0, 0. All right, nothing there. J 13, 0, nothing there. The only thing I have to worry about is this K hat. So I have -3 times -20. That's +60. But I'm going down into the left, so I have to think of the negative contribution here. So this will be plus minus 60 K hat inch pounds. I basically have like 3 negative signs when I go down into the left here. So it's going to ultimately result in a negative. All right, so all said and done, my moment at A from the two forces there, -260 inch pounds K hat. Okay, so using traditional methods, that's what we get, and perfectly fine if that's how you want to go about it. That's certainly the right answer. Now let's look at utilizing our shortcuts instead to make this thing rain. Shortcut. Okay. So I have to think about the contribution to the moment at A from these two forces. And we go back up to our picture here. I'm going to sort of erase all this. And what I want you to notice is I want you to notice that each one of these forces has a line of action. And that line of action is for this 200-pound force, that is this length. And for this 20-pound force, that is sort of this line that sort of extends infinitely. All right, so, this is the line of action of that particular 20-pound force there. And what I want you to notice is that the perpendicular distance between the line of action of that force at C and the point A is just simply this height here. Right? That is the perpendicular distance between the force at point C and my point A. It'll be important later. Similarly, the perpendicular distance between point A and my force at B is this 10 inches here. Okay, we see that that's the perpendicular distance between the line of action of the force at B and the point at A. So with that in mind, let's use our shortcuts and think about what's happening here. Okay, so from force at B, the magnitude of our moment at A is the magnitude of the force at B multiplied by this variable D. And remember that this D is, let's be very particular about this. This symbol here is a symbol that represents perpendicular. So instead of writing it all out, I'll just use this symbol. Perpendicular distance from A to the line of action of the force at B. All right. So the contribution from the force at B is the force at B, we know is 20 pounds, multiplied by the distance to B from A in a perpendicular sense, that is 10 inches. Okay, so the magnitude of this particular force, 200 inch-pounds. All right. That's the contribution to the moment from the force at B. I still need my directionality, right? So for my directionality, I'm going to use the right-hand rule. And still think about standing at this point A, sticking my arm in the direction of the force. So if we all pretend that we're standing on this beam at point A, all right, pretend that you're a guy with your head here, or a girl, don't want to be discriminatory here. You're standing here at point A, and you're going to stick your right arm out towards that force at B. All right, so stand at point A, stick your right arm out towards that force at B, and you're going to curl your fingers in the direction of that force at B. All right, the direction that your thumb points should be into the page. Okay, into the page is the negative direction by convention. Which is the negative k hat. So from the force at B, the moment at A is our magnitude, 200 inch-pounds, in the negative k hat. Or more simply, negative 200 inch-pounds k hat. All right. Now remember, this is only from like the force at B. So if you want to, give yourself a little reminder that this is only the contribution from B, that might be something that you could do. Okay. Now I still have to consider the contribution to the moment from the force at C. The magnitude of the moment at A from the force at C is going to be equal to the magnitude of the force C times the perpendicular distance between A and the line of action of C. All right. In this situation, that here is the force at C, 20 pounds, times the perpendicular distance between A and the line of action of C. If I go back up to my picture here, here's the line of action of the force at C. I sort of like drew it already. The perpendicular distance between point A and the line of action at C is that distance there. Right? That distance is 3 inches. Okay. So back down here, times 3 inches. So the magnitude of the moment at A from this force at C is just 60 inch-pounds. I still need to concern myself with the direction. I'll use the right-hand rule again. So this time, I kind of want to stand in this direction. Stick my arm out in this direction here, and curl my fingers in the direction of the force, would be that way, to give us the indication of the direction. If you did that again, sort of sticking your arm down, curling your fingers in the direction of the force, your thumb would again be pointing into the page, which would be a negative contribution. So the direction again is this negative k hat. So that means that the moment at A from the force at C is negative 60 inch-pounds in k hat. And we can see that this is exactly what we got with the traditional method. Okay. So the contribution to the moment at A from C was negative 60 inch-pounds. And the contribution to the moment at A from the force at B was negative 200 inch-pounds. And that's exactly what we saw with the traditional multiplication, or the traditional methods, where we had 200 inch-pound contribution from force at B and 60 from the force at A. So it's the same thing, it's just a bit faster method. Now I sort of like slowed this way down so you could sort of understand what's going on with this shortcut calculation. But I'm hoping by the end of the class, you should be able to look at a system that looks like this and be able to quickly say, okay, the contribution to the moment at A from this force is just 10 times 20, it's 200 pounds. It's acting in negative K, negative 200K. Bang. This guy, 20 pounds, it's 3 inches away, perpendicular distance. So the contribution to the moment about point A from this guy is 3 times 20, 60, acting in negative K when I think about right-hand rule. So the total moment at A from these two forces, negative 260 inch-pounds at K. Bang. Okay, I don't even need to write that down on paper. I can just do it very quickly in my head and just say negative 260 K hat. I'm done. All right. Once you get the shortcut methods down, you don't need to do the, the determinant form anymore. It's kind of like overkill, right? So there you go. All right. Oh, I got 15 minutes. I'm debating whether or not I want to dive in on the next topic. Yeah, let's save it for next week. You have all of the tools in your tool bag right now to do the homework number 3. So do that this weekend. We'll break today, give you a little bit of a break on this Friday, and say thanks for coming. Moments, we still got a ways to go on our moment topics, but will be nice to take a little bit of a break today. So enjoy your weekend. We'll see you on Tuesday. Finger guns. Thanks, Arthur.